Okay, so good afternoon. I think now you can mark attendance, yeah, for the PT, yeah. Yeah. Okay, so we see for the next intake, next group. So just like PT, now PT 20. Okay, now for PT 20, yeah. Okay, the other one may join a bit late, doesn't matter, we proceed with ODL. Okay. Okay, for ODL, yeah. Okay, done, yeah. Okay, so for the PT and PT 20, anyone join late, you still can let me know now, yeah. Oh, okay. Okay. So stand by with your SS now, yeah.
Hello, sir. 100 cannot mark attendance.
Okay. Okay, I think yeah. But I think you next time you better email to help desk, maybe they can help. Yeah.
Yes, sir.
I can help, no problem, but you email to them is a bit better. Okay. Be done. Okay. So now okay. So for just now we discussed already the dummy variable, how to handle it here under the multiple linear regression. Of course here the dummy must be independent. Okay. So if dependent, different story. Dependent must be only can use 0 and 1. Yeah. Okay. And then depends on how many categories. Let's say 4 means 4 minus 1. Let's say 3, 3 minus 1. Always minus 1. Okay. Let's say 4 categories. You must create 3 dummy variables like that. Okay. Okay. So this is what we discussed until just now. Okay. Okay. So question. Okay. Wait. Okay. So if no question, now we continue with our discussion in this multiple linear regression. Okay. So So can you see the first point also linked to the one that we discussed just now? The non-metric variable can only be included in the regression analysis by creating dummy variables. Okay, discussed already just now. Okay, so this is about the variable, the variable transformation. Yeah, means do some adjustment. Okay, you do some adjustment on the dummy variable because this non-metric. Yeah, okay, therefore should adjust a bit. Because by definition, actually the multiple linear regression is for the metric data, right? Metric variables, right? Dummy variable can only be interpreted in relation to their reference category. Means let's say they are variable just now, yeah, urban, yeah, okay. So either urban or semi-urban. When you because urban got their own equation, semi-urban got one equation. Therefore, when you do interpretation, you must mention something. This is about the urban, okay? This for the urban respondent. Maybe this for the period where there's no COVID like that. Okay. Okay. So next will be not this is not going to cover. So but just mention like that. Okay. So we can add one additional polynomial term. This example, let's say beta 2 x power 2. You see that is. Yep. So this will represent another inflection point in the curvy linear relationship. Yeah, will be already a bit different. Yeah, because we only handle the multiple linear regression. Okay. So power 2 already quadratic. It's not linear. It's not linear. Therefore, it's curvy linear. So this quadratic can be also cubic, means power 3. Let's say beta 2 power 3, x power 3. Okay. So basically, this already good enough, yeah, to represent most of the curvy linear, yeah, relationship. Okay. So, okay. Okay. So let's say for this one, meaning that we should handle the incremental R squared, yet not the t-test. Yeah. If I add something, I think in the slide they didn't mention t-test. This is t-test. The significance of the individual coefficient actually is the t-test. Okay. Discuss a bit because we are going to see this also. Yeah, the multi-collinearity. I think yeah, in this chapter, I think should be today lah. Okay. Yeah. Okay. You see a bit multi-collinearity. Okay. Later we see now also maybe also quite detailed. Okay, we see now. Yeah. Okay. We see some idea. Not going to see too technical. Okay, some basic idea. Right. The problem is that in general we assume that means under the assumption of the regression, okay, assumption, yeah. So we call this classical linear regression model. Okay. Under the assumption, the x1 suppose independent from x2, independent from x3. Okay, suppose. Yeah. Okay. So if this one happen, what is the problem? You see the problem of multi-collinearity. Yeah. Okay. Is that they have some relationship between x1, x2, x3, the three independent variables. Example. Yeah. So example, x1 is equal to x2 plus x3. This happened in the previous module, not the last intake, not the MMDA module, because I also teach this for other module. Okay, so the student finds the I think banking students should understand. Okay, the student finds three independent variables. X1 is the total loan. X2 is the business loan. Okay, so X3 is the personal loan. Okay, therefore total loan is equals to business loan plus personal loan. Yeah, for a bank or a company, not for individual, but for the whole bank. You see, therefore X1 is equals to X2 plus X3. Of course, finally cannot get the result. Yeah, because of the perfect. This is perfect. Okay. The multi-collinearity, this case is perfect multi-collinearity. It's very bad. It's very bad problem. Okay. So finally, I advise the student to drop one variable and find another variable. Okay. So x1 equals to x2 plus x3 is a problem, and this problem will affect the t-test. This problem will affect the t-statistics. Yeah, r square are not affected, but t are affected. Example, yeah. And normally they will make the t-test not significant. Example, let's say if no problem, no the multi-coordinality problem, the t-test should be, the t-statistic should be 3.2. Beta 2 should be 3.51 like that. Example, beta 3 should be 4.2. Okay, suppose like this, yeah. But this problem, the problem of the multi-coordinality will will affect the t statistics. Example, make it become only 1.2, make it become 0.51, make it become, let's say, maybe 1.61 like that. Okay, because of the problem. Yeah. Okay. So this the formula or the method is based on the assumption that x1, x2 no relationship, but now they have relationship. So the method fail. The method not able to find the correct t statistics from the data. Okay. Okay. If no problem.
So, sir, how to detect this multi-collinearity? I mean, sometimes it's obvious, as you said, but if some variables are not so obvious, how to know?
Yeah, don't worry. You see this one first. Don't worry. We can use the VIF. Yeah, but this one confirm you will discuss. Yeah. Okay. Should be today. Should be today. Okay. So you see, therefore this one not reliable. R square still reliable. Yes, R square is for the overall model, but T test, T statistics is for the individual variable. So therefore, we should not examine the T test, but only use the R square. Okay. So that's why the statement is like this. Okay. So this we should actually use the incremental R square. Let's say R square they increase from 0.35 to 0.42, therefore it's good. So like that. Okay. Means the overall model is good. Yeah. But not to see the individual coefficient. Yeah. Okay, because of the high multi-coordinality. Okay. So don't worry, we're going to see the VIF. So it's okay, I can discuss a bit, no problem. VIF more than 10 minutes got problem. I mean the problem always there. Yeah. Perfect multi-coordinality is the worst. Okay. But let's say VIF is only 2 or 3, they still okay, we can accept. Okay, yeah, like that. But more than 10, consider a problem. Yeah, we cannot accept. Yeah. It's a benchmark, okay, for us to detect to examine the problem. Okay. Okay.
More than 10, that means they are 10 internal connected drivers.
Not like that. They actually also based on the R square. Okay, formula. Don't worry, you see formula in the shower. Yeah.
Okay.
No, 1 minus R square, J. Formula for VIF. You see the show bar, yeah. Okay. So okay, continue. Okay. So you see, these are the four assumptions here in the multiple linear regression. Okay. So linearity, we can testing this here using the SPSS. This one cannot. I can show you the diagram. Okay, the diagram is also quite interesting. Constant variance of the error terms. Okay, you see now. I show you two. Yeah. Okay. So this one is a problem heterodescity, something like this. Okay. So this is okay. This is not good. Okay. This is good. Okay. Good means homo. Okay. Homodescity. Okay. So the diagram will be like this. Let's say this is a regression line. Remember, it's a regression line. Okay. And then for the homodescity is good. Therefore, the variance will be always the same. Okay, I use different color now. The variance always will be the same. Yeah, like this. You can see, you think this way. Okay, you see from this way. Yeah, this is normal curve. Remember, this is normal curve. Okay, yeah, like this. Okay, here like this. You see the curve quite similar. Quite similar. Okay, x and y. Quite similar. Therefore, this one means is the variance homo means same. Yeah, same. Means equal variance. Equal variance. Okay. So now we compare with heteroscedasticity. Yeah. So hetero, we still have the line like this. Okay. So something like this. Okay, something like this. Okay. So something like this. So here can be the income. X can be income. Y can be the consumption. Okay. So I mean, but this is a fact. This is a fact. This is a real life. Okay. So for the low income, yeah, for the low income family, the pattern of their consumption should be quite similar. Meaning that most of the income will spend on the food and also rental. Okay, this is a fact. This is a fact. Okay. So not 100%, but in general, it's like this. Therefore, their consumption pattern not much different. Okay. So, but come to the middle and high. This is middle income. Yeah, middle, high income. Yeah, their consumption pattern will be different quite a lot. Some may like buy luxury car. Some buy luxury handbag. Some like that for travel. Can see will be different quite a lot for the middle and high income. Okay. Any question? Therefore, this is a heterodescity. Okay.
So you're saying that the variance at the different range, I mean the lower range is not the same as the higher range. So is the data at that area, right? At that range?
So it's a different group. Yeah, correct. Different income range. Their consumption pattern will be different. Higher, there more variation. This okay. Let's say you randomly take two family, low income, family 1, family 2. You can roughly estimate. Roughly, you should know how much they spend on the food. Maybe 60% or 70% on the food. Yeah, but this one is not easy for you to predict. You can see some may buy car 1 and 2. This one may focus on car. This one may maybe invest. Okay, the third one maybe they buy a handbag and so on and so forth. It's quite difficult for us to predict the high income people how much they spend on which area, which part, we don't know.
And this is not yet considered two different clusters because it's gradually becoming I mean increasing or decreasing, right? It's not considered cluster yet, right?
No cluster. We're not talking cluster. We're talking a problem under the classical. This one. This is the classical linear regression model. Yeah. Means let's say the data is constant variance. Therefore, it's homolegacy. Therefore, it's good lah. Yeah. So the error term different not much. Okay. But let's say this different a lot. Okay. So this is good. Homo. Means they made the assumption. Okay. This one they did not make the assumption.
So, sir, how we get this indicator from just now our output? I mean the output result. Where we see the indicator.
No, this one we just see like that, but we can do testing on this few 1, 2, 1, 3, and 4. This one cannot. We cannot do this using the SPSS. But you see,
SPSS cannot calculate.
Yeah, cannot. But the 1, 3, 4 can we can do it. Okay.
So by knowing 1, 3, 4, then we know number 2, right? Whether it's
not like that. But means if you want you okay, if you want you can do it using reviews. But I think will be a bit burden for you if you learn 3 software. Okay, you can do this one easily using reviews. Yeah. Okay, but maybe quite heavy, even burden for you if you learn 3 software. Now we focus only on 2 enough. Yeah, it's SPSS and also MOS. Okay. Okay, we see the.
So your point is if it's not a constant variance, so it's not good that we use for the prediction because we never know what the variance will go, right? I mean the point is the constant variance is on the whether we can use it for prediction or not, right?
Yes, correct. Because you are right. If not good, meaning that the result not good. Means result not too reliable. Therefore, you cannot use it to do prediction. Okay. But as you know, the 3 already consider okay lah. Already consider good.
Okay.
Okay. The third one is independent of the error term. Yeah. Meaning that the error term, okay, we can do like this, covariance between the x and also the error term is 0. Covariance is also correlation. Is similar if correlation. So correlation or covariance 0 means no relationship. No relationship means independent. Means independent variable and also the error term no relationship. Right? Okay. Another one, the error term must be normal. The error term must follow the normal distribution. Okay, 1, 3, 4 we can do. You're using SPSS. Either today or next class. Okay. So this is the 3 assumption. Okay. Oh, okay, we can do it now. Okay, yeah, we can do it now. Yeah.
Sorry, sir. Normality of the error term distribution means if the distribution is skewed, then we are not able to apply this multiple regression analysis. Is it correct?
Yes, yes.
Thank you, sir.
Yeah. Okay, so now we do this. Yeah. So now we're testing on the assumption. Okay, we do the graphical analysis. Okay. For this field. Okay. Okay. We do this now. Yeah. Using the same data. Okay. Using the same data set. Okay, we do it now. Yeah. Okay. We give you 10 seconds to open the data. Okay. Wait. Okay. Of course, there's the relationship in that, but by definition, heterodicity is for the variance. So of course, if there are same variance, also same standard deviation. Okay. So we can extend it into the standard deviation because we know we take square root of the variance, we will get standard deviation. Okay. Yeah. Now we see this. Okay. So for this one, analyze, regression, and then linear. Okay. Okay. Analyze, regression, and then linear. So now we use we can increase the independent variable, but the dependence still same. Yeah, the x17. Then let's say okay, we take 3. Yeah, 5, 6, 16. Means we got 3 independent variables. Okay, any question? Yes. Okay. Alright. Okay. So if no, now what we do, we go to okay 36, and then here nothing. Okay, plot here. Yeah, we want this. Yeah, normal probability plot. Okay, and then produce all partial plots. Okay. Okay. So you want these two. Yeah. Okay. Okay. So if no question, so okay. If no question, then we click OK. Okay. It's okay. Another 5 seconds for you. Yeah. Okay. So now we see the output. Okay. So I think this one we already discussed just now. Yeah. Yeah. It's a similar thing on how to do the interpretation. Okay. Okay. Now we see this. Okay. So this is to see either the residual, the fault, yeah, the fault assumption, yeah. Okay, remember just now, the fault assumption. Okay, means you test to see either the error term is normal or not normal. Okay, you see this now, yeah. Okay. So PP plot, we suppose got one more QQ plot. It's okay. PP plot also can, yeah. Okay. 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 So so we see the left side is the expected cumulative probability, left side, yeah. And then the horizontal actually is the observed. Observed means is from the data. Okay, observed cumulative probability. Right. So roughly not too normal, but maybe still okay. If normal means the dots all actually must fall on the line. If it fall on the line, therefore is considered very, very normal. Yeah. Okay. So now roughly still considered normal. Okay. That's the test, the fault assumption. Okay. Any question, please? Okay. So if no, now we see next. Yeah. Okay. So this one is a partial regression plot. Yeah. So this one, yeah. Okay. Okay. Wait. Okay. So this one is, wait. Okay, this is to test the independence of the error term. Yeah, the independence if the error term. Okay. So you see, it's quite random. Yeah, means you cannot see any pattern. Example, okay. Okay. Let's say the data, the diagram like this. This is linear. It's a positive relationship. Okay. But now it's no pattern. Therefore it's random. Therefore it's good lah. Okay, it's good. Okay. So this is for the partial. Okay. Yeah. Okay. Any question? Yes. So far. Okay. Now we see. Next. Okay. I think we see the linearity later. Okay. I'm not sure why. Okay, later we see. I think this one part we can actually find the linearity of the phenomena. Okay, later we see how. Okay, so we continue first with this. Okay.
Sorry, sir. What is exactly this error terms mean?
No, error term is refer to the okay. Error term usually refer to this. This is the error term.
Got it, sir. Thank you, sir.
Okay. Continue. Okay. 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 So this one we done already a little bit just now. Okay. So we estimating the regression model and assessing the overall model fit. So we can do this using the the F test. Okay. So we select a method for specifying the regression model to be estimated. Okay. So we assess. Okay, the method means here can refer to the either enter or what. Okay, got few. We're going to see today. Yeah, I think today. Yeah. Yeah. Next. Okay, 3 o'clock. Well, yeah, next break will be 3 o'clock. Okay, yeah, I think it should be now. Yeah, okay. So you will see some. Yeah. Okay, some method. Yeah, such as enter. Okay, upon enter already done, you're going to see stepwise. It should be now. Okay, it should be today. Yeah. I mean this section. Okay. So we assess the statistical significance. It means we see the p-value to see whether the result is significant or not significant. Okay. The overall model means refer to F lah, the F test. You can test to see the overall model good or not good. Okay. Can it be used to predict or to explain the dependent variable? Okay. So we are going to see also how to detect the inferential observation. Yeah. Okay. Okay. So we see. Yeah. This is what I mentioned just now. Okay. Okay. So we see this is a variable selection approach. The first one is confirmatory. So okay. Remember just now we start the basic one. The x6 and also x16. They're affecting the satisfaction. Okay. Satisfaction, and then we just based on some theory. Yeah, some theory and also some article. Yeah, for us to choose these two. For us to choose these two independent variables. Therefore, we say that these two are affecting the dependent variable. Okay. Therefore, we call this confirmatory. Okay. Therefore, we done already for this You just use the basic one, the enter. Okay, the method is enter. Okay. Okay. Any question on this? Okay. So if no, now we see. Yeah, stepwise. Now, yeah, stepwise is more important for you. Yeah, it's assignment. Okay. Yeah. Okay. So you see, stepwise. Means now we are going to consider all the variables that are available. Yeah. Okay. So you are given a data set with all the data. Yeah. And you want to choose the best model, but you don't want to do testing one by one. Okay. So we see, you can also use combinatory example. Let's say you have A, you got 4. You have 4 independent variables. Don't worry, I will come back to stepwise. Okay. So for combinatorial, here, let's say you have 4 independent variables. Yeah. Model 1, you use all 4, A, B, C, D, 4 independent variables. The second model, you take A, B, C only. The third, you take A, B, D only. You see? Yeah. And then the fourth model, you take only B, C, D, and so on and so forth. You test all the possible subsets. You can do this manually. Okay. But stepwise is more powerful. It's like automation. The software will choose the best model for you. Okay. The software will choose the best model for you. Okay. So you see how the software work. Okay. How they choose the independent variable for us. Okay. We see this now under the stepwise. Okay, I think just now what student asked, yeah, correct, by default. By default is 0.05. Yeah. Let's say P means the alpha is 0.05 and 0.1. Okay. So let's say the P value is less than 0.05. Means the variable will be included. The system will test one variable each time. Each time only test one variable. Let's say they use the x1. Y is the independent. Y is dependent. X1 is the independent. They include x1 and then test. Can this x1 affect the y? Yes or no? Then they see the p-value. The p-value is less than 0.05. Therefore, now they include x1 in the model 1. But let's say the p-value is more than 0.1. Yeah, p-value more than 0.1. Therefore, the variable will be excluded. Okay, like this. Means only the significant variables retained in the model. Yeah, they will do this process. Yeah, continuous until they use out all the variables like that. Then they give us the final model. Okay, this is the process. Okay.
How about in between 0.05 to 0.1?
Okay, good question. Again, you mean 0.07?
Yes.
Okay, included, excluded. Okay, good question. Anything about this? Yeah, thank you. Okay, let's see how. But this is the procedure. Suppose that is. Yeah. Okay, but it should be excluded also. Yeah. Okay, we see now. Yeah, we see now. So, okay, we see now maybe use output can answer your question. Okay, we see the method now. Okay, so now we use all the metric variables. Okay, now okay. So analyze, regression, and then linear. Okay. Okay. So now what we do, we use all the metric variables. Yeah, from x5 until x19. X17 is still the dependent. Okay. Yeah. And we change the enter to stepwise. Okay, and then click OK. Click OK. Okay, done. So we see this is the p-value. I mean the process. You can see this model one, they include x18. Yeah, because x18 has the smallest p-value. Yeah. Okay. So finally, only 5 variables here in the model. Yeah. Each time they only include one variable. Altogether, 5. So the R square also keep increasing, but actually not too important. Yeah, we see. Okay. So we see the ANOVA. Therefore, we see the p-value all smaller than 0.05. Yeah. Okay. So the first model only one variable. Yeah. Okay. The p-value is very, very small, less than 0.001. They're all actually small. You see the last column, the rightmost. The rightmost column, they're all actually very small. Yeah. Okay. Even the f value drop doesn't matter, but still significant because p value is very, very small. Okay. So we find this variable, this model, you got five variables here in the final model. I mean 5 independent variables. Okay, so this is for the f test. Yeah, ANOVA, therefore f test. You see the f. Okay. Now for the t, actually is also okay, less than 0.05. Constant not too important. Don't worry about this. Constant even 0.46, but not important. We only see the p values. Yeah, for the okay. We only see the p value for the independent variables. Okay. Okay. So we see, yeah. So the third model, you got 3 independent variables, all less than 0.005. 4 also the same thing. Yeah, number 5 also, they are all small, yeah, less than 0.005. Yeah, okay. So we see here, they exclude, in the first model, they only include one variable. It excluded all other variables. Okay. So you see, therefore, even it's quite good, but still excluded at the beginning. Yeah, at the beginning. Yeah. So because the first variable, they have the smallest p-value. Yeah, I mean for the p-value for the t test. Yeah. Okay. So they choose that's what they choose. Okay. So okay.
So can we conclude that the 0.05 is the cutoff?
Yes, correct. This one, at least some students asked me just now also, is by default. Yeah, it's cutoff point. That's correct. It's correct. Okay. Okay. So now I can answer the question. Can you see here? 0.068 also excluded. Okay. Yeah. That means at the beginning, they use 0.05 and 0.1, but finally, even more than 0.05 also excluded. Can you see here? They did not consider this, even 0.068. Okay.
Okay, sir.
Okay. Okay. So you can see the final model is considered quite good because it's quite normal. You can see not some we still got some data point is outside the not fall on the line. Yeah, but it's quite good also. Yeah. And then also no pattern. Yeah, therefore it's independent. Okay. Okay, so this is the stepwise. Yeah.
So I saw in the excluded variables there is this collinearity statistic tolerance. So just to understanding, because this is something like an indicator of collinearity, how to read this?
Okay. So actually, we are going to see this in a short while. Don't worry. Yeah. So
Okay.
okay. I think all should be quite large. Yeah, we see also now. We see now. Is it should be quite large? Okay. Yes, correct. It's quite large. Yeah. Therefore, no problem. Yeah. Basically, the cut-off point is 0.05. Yeah. No, 0.1. 0.1. Yeah. So the tolerance is 0.1. This will link to the multi-causality. We see this in the short while. Okay. It's okay. I can discuss now. No problem. So we are going to, because we need to take something from the software, then we can get the VIF. VIF more than 10 means got problem of the multi-causality. Okay. And VIF is equals to 1 over tolerance. Is equals to 1 over 1 minus R over 2. Okay. Actually J. Yeah. Okay. So okay, you see this now? Yeah. Miss J, let's say J is equal, Miss J is the variable. Yeah. We can find the VIF for each independent variable. Okay. So let's say J is 1, VIF 1. Therefore here is 1. Okay. So you include this value, let's say it's 0.2. Yeah, 0.2. Therefore, what you get? Operator?
5, right?
No. It's 1.25. Therefore, it's okay. No problem. Because VIF is less than 10. Okay, therefore, no problem. Okay. But let's say tolerance is small. Example, 0.06. Okay. Therefore, 1 over 0.06, you get 16.67. Already more than 10. Therefore, no problem of the multi-causality. Okay. Okay. So this is formula, but actually it's very easy for us because we can use the software here to get the variance. Yeah, variance inflation factor. Okay. Okay. Don't worry. It's in the short while we see. Yeah. Now continue. Okay. So we done already. Yeah, for the stepwise. Okay. So we see now for the forward inclusion. Yeah, and also backward elimination. Yeah. Okay. So we see for the stepwise, the variable not removed once included. Right? Okay. So where is it? Okay. So this, let's say this the first variable likely to recommend. Yeah, this variable already in the model. Therefore, whatever happens next, they're not going to remove this anymore. Okay, this is stepwise. But then we see the second method. Yeah. Okay. Actually, third lah. The third. we discussed already, enter. Now stepwise. Now we see the third method now. Okay. The third method, forward inclusion, yeah, and also backward elimination. Okay, now. So therefore, the model, the variable already included, but can be also eliminated in the next model. Okay. So we see this now. Yeah. Analyze. Regression. Linear. Okay. You still use the same model, means you include all the independent variables. They're from all the metric independent variables. They're from the data set, but we change the method. Yeah. Okay. So to forward. Okay. This is forward. Okay. So then okay. Okay. So you see the forward, the method, the criterion of the F to enter. Can you see we use the p-value? Yeah, p-value of F, not T. Yeah. Okay. Yeah, F is correct. Okay, F. Yeah. So less than 0.05 we enter. Okay. So likely to recommend. And then second is the complaint resolution. Yeah. Okay. And then after this, likely to purchase. And then Salesforce image. They include the borderline, but for this one, they also did not remove it. Okay. But sometimes it's by chance. Yeah, not because they did not follow the rule. Yeah. This means the variable is always have the p-value of less than 0.05. Therefore, always in the model. Okay. So
So is it meaning to say that the forward and stepwise, what is the difference? I'm not really, I'm a bit confused on this.
okay. Okay, we see. Okay, so you see the difference is that the stepwise they may actually remove a certain variable. They already in the no, the stepwise they're not going to remove the variable once the variable is selected in the model. But for the future, for the forward, they may actually remove the model, the variable. Okay, maybe. Yeah, see, this is different. Yeah. Okay. Example, I give you example. Okay. Stepwise and also forward. Okay. Let's say in the first model, you include x2. Yeah, here you also include x2. Yeah. But in the second model, x2 confirm. S2 confirm must be in the second model. Yeah. Okay. X2 confirm must be in the second model. Yeah. But in the forward X2 maybe in the second model, maybe not. Maybe yes, maybe not. Okay. Yeah. You see, variable not removed once included in the regression equation. Yeah, but the forward and backward they may remove it. Okay, later. Okay, it's the difference between this stepwise and also the forward. Okay, you see.
So meaning to say if the stepwise the variables not removed means if we create our equations, all the removed variables will be inside the equation as well.
No, not like that. Not like that. Okay. Wait, is stepwise? No, it's the enter. No. Wait. Suppose this is stepwise. Wait. It's correct here. Okay. So you see they include the variable one variable each time. They got many models. Model 1, they include x18. They found that is significant because the p value for the f is smaller than 0.05. Therefore, now likely to recommend already in the model 1. Okay. Now step 2, they include one more variable, x7. And then the p value of the f is still less than 0.05. Therefore, x7 also included like that. Okay. And let's say, okay now.
So, sir, it's like stepwise, as you said just now. It tests every variables, and then he knows the p-value of each variable. Then I think that for the model 1, it just select the one with the lowest p-value. And
Yes,
then for
correct.
model 2, it start adding up the next lowest p-value until model 5.
Correct.
But when it will stop is why it stop at the model 5 is it should be a cut value like 0.05, then it's cut at there, right?
But then you see they include one more. From here, they can exclude it. From this list, they can actually find one more. Yeah. Okay. Competitive pricing. Yeah. They're not going to consider this because it's 0.06.
Yep.
Yeah. So, but when they are in model 4, they may include one more, a few more borderline. 0.001. Can you see? So price flexibility. Actually, support is still smaller because they may have a 0.0023 like that. It should be smaller than this. They say they choose the product line. You include in the model 5. Okay, product line. Okay.
Okay. So for the forward one, I think you also will check the variables. I mean the p-value for each variables, and it may start with also the lowest p-value. But for the second model, then it may not include the one that already included in the model 1.
They include the likely to recommend. For now, they got 2. In the model 2, got 2 variables. They run the testing.
Yep.
Okay, and then they get the p-value also very small. The
Yep.
p-value for f is also small.
Okay,
Therefore,
when it combine. Okay.
yeah, therefore they find a third one like that. Just step by step. Therefore it's stepwise.
Okay.
So can I say that the best one is a stepwise, right? Compared to forward and backward.
You can say so. Yeah, you can say so. Yeah. Alright.
Maybe stepwise is the advantage is more time saving, right? Since it will keep on adding up. Like forward and backward, it may try different combination and more time consuming.
Actually more efficient. You can get the result a bit faster. Yeah, let's say got many variables. Yeah, because you see the variables not removed once included in the regression equation. Yeah. So they test a new one. The old one already confirmed must be in the equation. See in the output not here. Not here. It's correct here. You see the model 1 confirm got likely to recommend. 2 also likely to recommend. Because already enter, therefore forever will be there. Likely to recommend. 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 Yeah. Okay. So the 2 also same. Yeah. Complaint resolution already there. Therefore third model must be there. You can see? Yeah. Yeah, like that. Okay. So this is the yeah, you must know these are the stepwise.
Okay.
Okay, any question? Yes. Okay. So if now we see next Okay. Okay. So it's okay. You still can ask question, but it's okay lah. I think I give you the question now in the chat box. Officially, I will upload tomorrow. Yeah. I give you the question now. If you have time, you can go through it and ask me question after the break. Okay. I do it now. Yeah. I give you the question paper now, before so that you know how to ask question. Yeah, for the stepwise. Yeah. So you can ask now. Yeah. I mean, you can ask after the break. Yeah. Now you continue with other things. Yeah. No, sorry, I cannot give you this. I forgot one thing. It's okay. It's very fast. Yeah. Okay. Okay. So now I give you the question paper, the assignment. Assignment. So officially, I will upload tomorrow and then set the date. Take some time actually to do the setting, but before I do it tomorrow. Now I give you the question. Yeah. Now. Yeah. If you want, you can ask question. Ask me question after the tea break. Okay. Okay. Now we continue with the still in the multiple linear regression. Oh, okay. 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 So I think we can ignore the hierarchical. Okay. We see next. Yeah. Okay, because hierarchical is more to, okay lah, do a bit promotion, yeah. So it's more to MDA, yeah. Those data science, you may consider to take this module, as your elective. MMDA, no choice, yeah, for the data science student, it's compulsory. This is optional, yeah, up to you, yeah. So this hierarchical regression, yeah, in multi-level data analysis. Okay, so yeah. Okay. I think AI student no need, but MMDA is optional for you. Yeah. Okay. So continue. Yeah.
So, sir, just to ask, in the SPSS, in the method, so just now we try stepwise and then forward. So I think the backward also is to be similar like the forward one, right?
Yes, correct. Quite similar.
And then one more is a remove. The remove
It's okay.
is,
You know they want. You know they want.
oh,
Okay, three already. 3 or 4 already enough. Okay. Yeah.
okay.
Okay. Next. Okay. So now we see some terms. Correct? There's some terms. Yeah. So regression analysis terms. Yeah. So this one discussed already. R square is the officially is the coefficient of determination. Okay. Okay. So unexplained variance is the residual or error. You also refer to the this quick one. Yeah, a quick one. So refer to this term, the error term. Okay. Some textbook call it residual. It therefore can be also R. Yeah, R or E. Excellent. Yeah. So adjusted R square reduce the R square by taking into account the sample size and the number of independent variables. Okay, discussed already. Okay, just now. So therefore, normally, the adjusted R square will be smaller. The value will be smaller compared to R square. Okay. Okay. So therefore, it becomes smaller. Yeah, it becomes smaller if you have less observation. You have independent variable. It's a ratio. Not only see the observation, but it's a ratio of the observation to the independent variable. Okay. So this one not too important, but in general, smaller is better. Okay, because they calculated based on the error. Yeah, smaller is better. Okay. So therefore, smaller means smaller means lesser, smaller error. Therefore, accuracy will be higher. Okay. So estimate the relation of the dependent value around the regression line. Okay. Total sum of square. Total sum of square is a total amount of relation that is yet to be explained here by the independent variables, the SSs. Yeah. So, okay. Basically, sum of square regression SSR divided by SST, we will get R squared. Okay, this is how you can compute the R squared. Yeah, you take SSR over SST. Yeah, you get R squared. Yeah. Okay. Therefore, it's a percentage of variation that can be explained here by the independent variables. Okay. So, okay. So sum of square error is a variation here for the from the error. Therefore, it's not too good. So in general, this is a fixed number. This is higher is better. This lower is better. Okay. So means you know this is how we compute the R squared. Yeah, based on here. Okay. So discussed already. Okay. This is how we can compute the error. Yeah, the error lesser is better. Yeah. So therefore, the line should be the regression line that we get should be quite close to the data point. If too far, means not good. Okay. Too far away, means not good. Okay. Any question? Yes. So far. Okay, so if no, yeah. What do you mean by reference? Yeah. How to complete? You can ask question after the break. Yeah. Okay. I think quite straightforward. Yeah. Of course, you must find data first. Okay, you must get data first. Okay. So I mean, if you are fast, you get data, you can start to do the number one already. Okay, the question number one. But officially, I will upload it tomorrow here to the Moodle. Okay. But don't worry, tomorrow, the one that I upload tomorrow and just now actually same thing. Okay, same thing. Okay, we continue. Okay. Okay. Don't worry too much on this thing. It's too long, but in general, F is much more important compared to R squared. Okay. They use very academic language. It's not wrong. Yeah. But in general, F is more important than R squared. Okay. So therefore, still use 5%. Yeah, is the default. Yeah, cut-off point. Yeah. Okay. R square will be in between 0 to 1. Yeah, it's a percentage. Yeah, 1 means 100% can be explained by using the independent variables. But normally not the case. Normally should be less than that. Okay, less than 1. Okay. Okay, let's see. You see this point? Actually, they say that R square is significant, but doesn't mean it's a particularly significant. Yeah. Okay. So therefore, actually still the F is important. Yeah, F is much more important. Okay, compared to R square. Okay. No question. Now we see. Yeah. You see a bit more, then take a break. Okay. Okay. This is something we discussed already a little bit. Now we see a bit more. Okay. So, okay. Therefore, theory must be guiding factor in evaluating the final regression model. Yeah, of course, not necessarily theory, can be also some research done by other people. Okay, means journal article. So you see the first, this one discussed a bit just now, complementary specification. Meaning that you look for a journal or theory, you find some variable. You included in your in your model, you do testing. Okay, so that's it. Yeah, you did not choose anymore. You did not allow the. This you fully control. You fully control on the model. Your model got 5 independent variables. So that's it. That's what you get in the result. Okay. So it's the only method to allow direct testing of a pre-specified model. Okay. If you specified it earlier. Okay. Okay. So yeah. Sequential search, example stepwise. Yeah. So forward and backward. Okay. While maximizing the predictive accuracy, represents completely automated because you allow the software to choose the best model for you. Okay. So you're leaving the researcher almost no control about the final model. You don't know what model you are going to get. Okay. Okay. So of course it's still possible. Let's say you got some project, okay, from some company. Yeah, therefore you use the variable that given by them. Okay, yeah. So combinatorial estimation discussed also just now. Let's say A, B, C, D. You can start model 1, you do everything. Model 2, you take only A, B, C as the independent variable. Yeah. Second model, you take only A, B, D. Yeah, and so on and so forth. Okay. So you consider all the possible models. Okay. Okay. So still remove control from the researchers in terms of final model. Yeah. So even though the researcher can view the set of roughly equivalent model in terms of the predictive accuracy. Okay, give you an example also. I'm not saying it's very good, but this is also some example of the combinatory estimation. Okay, show you now. Yeah. Okay. Okay. So means here I actually also use this similar method. I run some models. Yeah. In my thesis. Okay, not finish. Okay, not finish. Still in the process. Okay. Okay, can you see something like that? Okay. So got few models. Like that. Okay, so consider some possibility. Maybe not 100%, but some alternative. Yeah. Okay. So here I remove this term. Yeah. FDI and QTY. Don't have. But here also I remove QTO, QTY. Okay. So some examples. Yeah. Okay. Now, no single method is the best. Okay. So, okay. Okay. So this anyhow still must refer to some theory in terms of the interpretation. Okay. Okay. So 3 questions about the statistical significance, and also of any regression coefficient. Yeah. So first we see the p. This is easy. We just see the p value. Yeah. Statistical significance. only see the p-value. The sample size, is it significant because of the large sample size? Let's say 1 million. Okay. Is the significance due to sample size? Yes or no? Okay. If yes, then you should do something. Okay. So n1 equals to 5,000. The method I mentioned few times already. Okay. So and then also must actually also discuss some practical significance. Yeah, and then not only statistical significance. Okay. Just explain it logically. Don't see okay p-value you are very happy. Okay. Means let's say you use stepwise. Okay, you see p-value all very good. Then you must know also the reason how or why this independent variable can affect the dependent variable. Okay. Okay. Any question so far? Yes. Okay. So if no, please see you at now. Okay. 3. Yeah, our class until 4:30. So now 2:49, 2:50, 2:50 to 3:20. Yeah. Okay. So 3:20. Oh. Okay. Yeah, it's okay. Yeah. Okay. So see you at 2:30.
Yeah, thank you. See you, sir.
Okay. If no question, so 2:30. Yeah, 2:30 until 4:30. Okay. So okay. See you at the hour. Yeah. Thank you.